So now we know how to find the correlation coefficient given a set of bivariate data. But in practice, most of the time we are doing this for sample data. We only have a few data points from our sample. We do not have data for the whole population. What we would like to be able to do is to perform a hypothesis test to determine if the strength of the correlation of a sample is strong enough to suggest there's a correlation for the entire population. If the correlation from a sample is strong enough that we can use that correlation to model the behavior for an entire population. Okay? So we use a couple different symbols here. We've already learned R, and we usually use R to represent the correlation coefficient of a sample, of sample data. So this is our correlation coefficient of our sample data. We use a different symbol for the correlation coefficient for the whole population. We use the Greek letter rho. So this is the Greek letter rho. Spelled R-H-O. Notice it looks like a P. It is not a P. This is a P. This is a rho. A little bit different. Okay? This is the symbol we use to represent the correlation coefficient for an entire population. Should have the word of here also. Okay, so we have two letters here, R and rho. Rho is the thing that we actually want to hypothesize about. We want to know if there's a correlation for the population. But R, the correlation coefficient of a sample, that's what we can actually calculate. Okay, so let's state our hypotheses for a hypothesis test of the correlation coefficient. We have two hypotheses. As usual, our null hypothesis and our alternative hypothesis. Our null hypothesis, or our default hypothesis, is that there is no correlation, that the variables are unrelated, right? Remember, there is no correlation when the correlation coefficient is 0. So our null hypothesis is that in the population there's no correlation. The alternative hypothesis is that there is some linear correlation. If rho is anything other than 0, there is at least some degree of linear correlation. So those are always going to be our hypotheses when testing the correlation coefficient. Okay. Now, when testing the correlation coefficient, we are going to use T-distribution. So our sampling distribution is a T-distribution we use n-2 degrees of freedom. That's a little bit different than usual. It's not n-1, it's n-2. Okay? That has to do with the fact that we have bivariate data, and we are looking at whether the data, if there's a linear correlation with the data. Generally, you need 2 points to determine a line. So that's kind of where that 2 comes in. Okay? And then our test statistic is going to be T equals our sample correlation coefficient R times the square root of n-2 over the square root of 1 minus r squared. That's going to give us our t-score. Okay. Notice that because the alternative hypothesis uses a not equal to symbol, that when we're testing the correlation coefficient for a population, we are always going to be doing a two-tailed test. And as usual, once we calculate our t-score and use that to find our our p-value using a two-tailed test. We're going to compare our p-value to our level of significance alpha. If the p-value is smaller than alpha, then that means that the evidence we have is strong enough to reject the null hypothesis and accept the alternative. In this case, that means we reject the idea that there is no linear correlation in the population. We conclude that there is at least some degree of linear correlation in the population. We conclude that the alternative hypothesis is true, that rho is not 0, which means that the correlation between the data is statistically significant. Okay. On the other hand, if the p-value is greater than or equal to alpha, then it's not that unlikely thing to happen just by chance, so we don't have enough evidence to reject the null hypothesis. We do not have enough evidence to conclude that the population correlation coefficient, rho, is not 0, and that the data is statistically significant, that the correlation is statistically significant. We just don't have enough data to conclude that. The steps involved in a hypothesis test are still the same as they've always been. Okay? So hypothesis test steps. 1, we're going to state our null and alternative hypotheses. We just discuss what those are going to be for a test for the correlation coefficient, right? The null hypothesis will always be, for this kind of test, that the correlation coefficient of the population, rho, is equal to 0, so that there is no correlation. The alternative hypothesis, when you're testing the correlation coefficient, is always that the correlation coefficient for the population, which is rho, is not equal to 0. So there is some degree of correlation. Those are always going to be your hypotheses for this kind of hypothesis test. 2, assuming the null hypothesis is true, identify the sampling distribution. We saw in this case that we're going to use a t-distribution with n-2 degrees of freedom. And we saw that we have a special way to calculate our test statistic t. Okay? Once we've identified that sampling distribution, we've calculated the test statistic, we can find the p-value. In this case, we have a not equal to symbol for the alternative hypothesis. So when we're testing the correlation coefficient, to find the p-value, we'll always do a two-tailed test. And finally, step 4, we have to make a conclusion. Draw a conclusion.